All right, in this video I'm going to talk about homomorphisms. Now, we've talked about isomorphisms, which is similar. Now, the difference between homo and iso means identical, and homo means like. For instance, homogeneous means that the consistency is like all the way through the material. So homo means like. So in some way, homomorphism is not quite as strong as isomorphism, but there is some similarity. Groups that are homomorphic are similar in some way, but they're not as identical as isomorphic groups. All right, so here it says, for instance, isomorphism. If you have two groups that are isomorphic, they're basically the same group. You're just using different letters to represent what behaves the same way. For instance, here's this example, Z4 and the cyclic group generated by I, which is the fourth roots of unity. And we found this mapping. It's a one-to-one onto mapping, which preserved the operation. All right, now, so this is Z4 with I. Let's consider Z8 and I. All right, so let's look at the tables. Z8 is an additive group, and it has 8 elements. So here we have the table, and we also have the table for I, the multiplicative group of I, and we can see some similarities. For instance, here we have this diagonal pattern of constant elements, and we have the same diagonal pattern here. Let's see, so that's mentioned here. Like this pattern of 2's here matches the -1's and so on. So it kind of looks, if I just look at this first part here, it does look kind of similar to this one here, except here I'm going out to 6. If I tried to make this Cayley table here, it would not be closed because 3 plus 3 is 6. So there's some similarities, but there's some differences. Now, can we exploit this similarity to make a relation between these two groups? So here it says, let's try to create a function from Z8 to I which preserves group operations. Right, and we're going to make a here we're going to make an onto function. We can't possibly make a one-to-one function because Z8 has 8 elements and I has 4 elements. Okay. So if we want to make some function, it seems natural, as it says here, that 2 elements from Z8 would go to 1 element in I. So let's think about which 2. And here we're kind of flying by the seat of our pants. Let's just make this choice that 1, what goes to 1 is 0 and 4. What goes to I is 1 and 5. All right, let's remind me later. 1 and 5. What goes to -1 is 2 and 6. What goes to -I is 3 and 7. So here we kind of have an even spacing. This seems to be a regular way to associate elements of Z8 with elements of the cyclic group generated by I. Right. So let's take the Z8 table and start transforming. All right, so you get this table. We've replaced the elements of the Z8 table with the elements of the cyclic group generated by I that go to. For instance, this was 0, 1, 2, 3, 4, 5, 6, 7. 0 goes to 1, so I replace the 0 with 1. 1 goes to I replace the 1 with I. 2 goes to -1, I replace the 2 with -1, etc. And if you replace all the elements in the table, then this is what you get. All right, now here it says we remove redundant rows and columns and change the group operation. Now, for instance, this one row here appears twice. It appears here and it appears here. So I can just cross out this row. Right? This I row appears here and here. So I'm going to cross out this row. This -1 row appears here and here. I'm going to cross out the -1. Cross out the -I. Similarly, this one column appears twice. I'll cross this one out, this one out, this one out, this one out. Those are redundant. What I have here is now the same as the Cayley table for the cyclic group generated by I. So we have made some kind of relationship between Z8 and I. Okay. All right. So this function does do it. Now, what we have here is still this operation preserving property, that if we take this function g, which is now no longer one-to-one, but it is onto, and if I take g and I take the operation in the table for z8, and I take g of that, I'll get the same result if I take g of a and then do the operation in the cyclic group generated by I with B. So this is the operation in cyclic group generated by I. This is the operation in Z8. I still have this kind of operation preserving property, although I don't have a bijection anymore. So you remember, isomorphism means you have bijection and operation preserving property. Now here we have a function that's not a bijection, but we still have the operation preserving property. So what do we call this function? We call it a homomorphism, because the two groups are not identical, but they still have some likeness. Okay. Now we can notice some things, that in our function in this example, we did have the identity mapping to the identity, and we also had that the 0, 4, which mapped to the identity, was in fact a subgroup of Z8, right? Because 4 plus 4 is 0 in Z8. Right? So a subgroup of Z8 mapped to the identity of the cyclic group generated by I, fourth roots of unity. So that's one thing. And these sets were not subgroups. Now if you think about it, these sets are actually cosets of 0, 4. 1, 5 is the same as 1 plus 0, 4. Sorry, 2, 6 is 2 plus 0, 4. 3, 7 is 3 plus 0, 4. So these are cosets. Okay? So our cosets are mapping to different elements of the fourth roots of unity. And in fact, this is a normal subgroup of Z8. You can see that, of course, because the group's abelian. Okay. All right. Now, what I can do, since 0, 4 is a normal subgroup, and the set of cosets itself is a group, I can create the factor group, right? So let's look at the factor group, where we take the cosets of 0, 4 in Z8, and we take this result. Now, if you look at this result, and you think of the result for the cyclic group generated by I, in fact, you see a similarity. In this case, we actually have an isomorphism. You still get the same pattern. So you get 0, 4 goes to 1, 1, 5 goes to I, 2, 6 goes to minus 1, 3, 7 goes to minus I. If you make those replacements, this Cayley table agrees with the Cayley table here. So we actually have an isomorphism between Z8 mod 0, 4 with the fourth roots of unity. Okay. So somehow from our homomorphism we're getting an isomorphism. So here's another representation that these cosets go in a one-to-one onto fashion onto the elements of the cyclic group generated by I. Okay. Now we've seen some properties of this particular homomorphism which may or may not be true for all homomorphisms. Okay. In this case we could, all right, so in this case we had a function that was onto, but we could actually have a function that's neither one-to-one nor onto. In fact, this function here that takes 0, 2, 4, 6 to 1 and 1, 3, 5, 7 to minus 1, it doesn't go to all of the fourth roots of unity, but only 1 and minus 1. Okay. And we can see that if we relabel this Cayley table for Z8 according to the mapping, that is 0, 2, 4, and 6 we replace with 1. 1, 3, 5, and 7 we replace with minus 1. We get this table. If we cross out redundant rows and columns, then we'll just get this table in the corner here, which is the table for 1 minus 1, the table for the multiplicative table for this two-element group. So we have the same result, that this relabeling gives us the Cayley table for the range of the function. Okay. So we have the same, and we can look at the same things. We actually have the operation is preserved. Again, this is the operation in Z8, and this is the operation in the group generated by minus 1. Okay. And we get these same observations we had before, that the set in Z8 that maps to the identity of, so this shouldn't be I, this should be -1, sorry. This is still a subgroup. If you think about this, all of these even multiples will add into themselves, so it's a closed subset of Z8. It's a subgroup. Okay. On the other hand, this is a coset. Okay. So I can say the set of elements that map to 1 is a subgroup. The set of elements that map to -1 is a coset. Okay. We can also use this mapping to create an isomorphism, just like we used the previous mapping G to create this isomorphism between the cosets of Z8 and the elements of I. Now in this case, we take the cosets of this 4-element group in Z8 and create an isomorphism to the cyclic group generated by -1. All right. So let's go down. All right, so let's stop there, but we see some good properties of homomorphisms. We'll continue with the next video.